Let us now solve the last two problems from the chapter of circles from exercise 9.3. So the last two problems are question numbers 11 and 12. So we will be attempting these two problems today in this video. So question number 11, we are given that ABC and ADC are two right triangles. So that means these are right angle triangles. So we have a triangle ABC, which is this triangle over here, ABC. So the triangle on the left here. And then we have another triangle ADC, so that's the upper triangle over here, ADC. And we are given that these two triangles have a common hypotenuse, the side AC. So this side AC is the hypotenuse for both these triangles. So the triangle ABC has hypotenuse AC, and similarly the triangle ADC also has the side AC as its hypotenuse. So the common hypotenuse is AC for both these triangles. We are asked to prove that the angle CAD and the angle CBD are equal. So the angle CAD is this angle marked over here, and the angle CBD is the angle marked over here, and we are asked to prove that these are equal. Okay, how can we proceed with this particular problem? Okay, there is no circle mentioned in this question. It only says that there are two right triangles with a common hypotenuse AC. So why do we bring in the circle, and how can we bring in the circle here? Okay, the fact that it's a right angle triangle, so that means the angle opposite to the hypotenuse is the right angle in a right triangle. So we have this particular angle, which is the angle ADC, as the right angle in the triangle ADC, because that is the angle opposite to the hypotenuse. So we know from the construction of a right angle triangle that the hypotenuse is opposite to the right angle. So we know AC is the hypotenuse, so therefore the angle opposite to the hypotenuse, that will be the right angle component of that right triangle. Similarly, for the triangle ABC, AC is the hypotenuse, and the angle opposite to the hypotenuse, which is the angle ABC, so that is also going to be 90 degrees. So we have this angle ABC and angle ADC are both 90 degrees from our construction, right? So angle ABC equals angle ADC equals 90 degrees. So these are angles which are opposite to hypotenuse. So okay, and we know the angles opposite to the hypotenuse are 90 degrees. Now if these angles are 90 degrees, we can consider the side AC to be the diameter of the circle, because we know that the angle subtended in a semicircle is 90 degrees. So we can now construct a circle with this line AC, the side AC, as the diameter of the circle, and then we have the angle subtended by the semicircle as 90 degrees. So the angle ADC is the angle subtended by the lower semicircle on this side, and the angle ABC is the angle subtended by the upper semicircle on the upper side here. So this is where the circle comes in, because we have a 90 degrees angle opposite to the common hypotenuse AC. So we can treat this common hypotenuse AC as the diameter of a circle, and now we can go on to show and prove what we are asked to prove. Okay, so we have now constructed a circle with AC as the diameter of the circle, and we now have the angle ADC and ABC as the angle subtended by the semicircle, which are 90 degrees, and we already know that these angles are 90 degrees. So therefore we treat the side AC as the hypotenuse, as the diameter of the circle. So we first construct a circle with AC as the diameter, and we are able to construct the circle with AC as diameter because we already know that the angles opposite to AC are both 90 degrees. So we have now taken AC as the diameter of the circle. Okay, so next thing what we can do is we will join BD Okay, so the next construction is to join BD. So join the points B and D, which is shown by the dotted line over here. And now we have to show that the angles CBD and the angles CAD are equal to each other. So how can we show that? We can clearly see once we have joined the points B and D by the line segment BD, what we see is that the angle CBD is subtended by the chord CD at the point B, and the angle CAD is also subtended by the same chord CD. So angle CBD and angle CAD are subtended by the same chord CD, or the same segment of the circle CD. So we can now say that angle CAD is subtended by segment CD of the circle, and similarly angle CBD is also subtended by the segment CD as well. So we know from our theorem that the angles subtended by the same chord or the same segment at different points on the circle are equal. So therefore we can state that angle CAD is equal to angle CBD, and that's because they are both angles subtended by the same segment. And we know from our theorem that the angles subtended by the same segment are equal. So hence we have proved that the angle CAD is equal to the angle CBD, which are the angles shown by the black arcs over here. Okay, so we have hence proved what was required to be proved. Okay, so we say hence proved. Okay, now in this particular case we have drawn the two triangles in such a way that the two triangles are on opposite side of the common hypotenuse. So we have the triangle ABC on the left hand side of the diameter AC, and the triangle ADC on the right hand side of the diameter AC. So this is the first style of construction, or first case of construction. So we'll call this approach as case 1. Okay, so this particular method of solving this particular problem, we'll call this as case number 1. Okay, we have solved it by constructing our triangles ABC and triangles ADC opposite to each other, such that they are on opposite sides of the diameter AC. But we could have constructed these two triangles such that both the triangles were on the same side of the diameter AC within the circle. And that gives us another method of solving this problem, which we will also attempt to solve and see what happens. So this is the new construction over here, where we have the two triangles ABC and ADC to be on the same side of the diameter AC. So we'll call this approach of solving the problem as the second case. So we'll call this as case 2. So again, we are asked to prove that the angle CAD and the angle CBD are equal. So we are given that we have two right angle triangles ABC and the triangle ADC with the common hypotenuse. The common hypotenuse is AC. So hypotenuse is the side opposite to the right angle. So we have this as our right angle ADC over here. And similarly, hypotenuse is the side opposite to the right angle. So therefore, ABC is also a right angle here. And we see that both these triangles, triangle ABC and triangle ADC, are both on the same side of the diameter of the circle AC, and which is the side AC is also the hypotenuse of both the triangles, triangle ABC and triangle ADC. Okay, now with this construction, how can we prove that the angle CAD is equal to angle CBD? So clearly, first of all, we have angle ABC as 90 degrees and the angle ADC as also 90 degrees because these are both angles subtended in a semicircle. Okay, we have the segment AC as the semicircle because AC is the diameter here. So this segment AC of the circle is a semicircle, and the angle subtended by the semicircle, which is angle ABC and also angle ADC, are both equal to 90 degrees, which we know. So angle ABC equals angle ADC equals 90 degrees because these are angles subtended in a semicircle. Okay, are 90 degrees. Okay, so we have this information with us, and to prove that angle CAD and angle CBD are equal, we will make a construction by joining the points B and D. Okay, so the construction that we will make is to join BD. So we have now joined the points BD, which is shown by this dotted pink line over here. And now we have to prove that the angle CAD and the angle CBD are equal. So let's see, where are those angles? So the angle CAD is this angle over here, CAD, which is the angle between this red and blue line over here. So which is this angle, that's our CAD. And the angle CBD is the angle between the red and the pink line over here. That's our angle CBD. And clearly we see that angle CAD is subtended by the segment CD or by the chord CD at the point A. Similarly, the angle CBD is also an angle subtended by the same chord CD or by the same segment CD of the circle. So we have now, once we have joined BD, we can clearly see that angle CAD and angle CBD are subtended by the same chord or segment DC. Okay, and we know that the angles subtended by the same chord or by the same segment in a circle are equal. So therefore we have angle CAD equals angle CBD, and that's because angles subtended by the same segment, or you can also say by the same chord, are equal. Okay, hence for the second case also, where we have done the construction of the two triangles in a slightly different way, such that they are both on the same side of the diameter AC, again we have proved here that the angle CAD, which is this angle, and the angle CBD are equal, which is what we are asked to prove. And clearly we see that these are both angles subtended by the same segment DC of the circle or by the same chord DC of the circle. Okay, so we say hence proved. Okay, so that's the solution for this problem, which could have been approached in two different ways based on how we constructed the two right angle triangles which had a common hypotenuse AC. So we have now the triangle ABC with the hypotenuse AC, and also the triangle ADC with hypotenuse AC. But now in this construction of case 2, we have both these triangles on the same side of AC, but in the previous case we had the two triangles ABC and ADC on opposite sides of the hypotenuse AC, And then the hypotenuse also, we have shown that it can be treated as the diameter of the circle, since the angles subtended by the semicircle are 90 degrees. Okay, so that's the solution for question number 11. Now we'll move on to solve the last question from this exercise, which is question number 12. And what we are asked to prove is that if we have some cyclic parallelogram, we have to show that it is a rectangle. So we are given a parallelogram ABCD, and we are given that this parallelogram is a cyclic parallelogram, and we have to show that this is a rectangle. So we know from the property of parallelogram that the opposite angles in a parallelogram are equal. Since we are given that ABCD is a parallelogram, opposite angles must be equal. That means angle A must be equal to angle C, and similarly angle B must be equal to angle D. Why is that? Opposite angles in a parallelogram are equal. The next bit of information given to us is that the parallelogram is a cyclic parallelogram. So that means for a cyclic parallelogram, or for any cyclic quadrilateral for that matter, whenever we say cyclic, it means that the sum of the opposite angles is 180 degrees. So we say, since ABCD is cyclic, angle A plus angle C is 180 degrees. Similarly, angle B plus angle D is also 180 degrees. Again, that's because sum of opposite pair of angles in a cyclic quadrilateral is 180 degrees. So let's write that. So now, combining these two pieces of information, that the sum of the opposite angles is 180 degrees and that the opposite angles are also equal, so we can now say that therefore angle A is equal to angle C equal to 90 degrees. Since we have angle A and C to be equal, and also we have angle A plus angle C to be 180 degrees, so therefore we have angle A to be equal to angle C, which is that both are equal to 90 degrees. So similarly, we can also say that angle B is equal to angle D, and they are both equal to 90 degrees. So 90 plus 90 degrees is 180 degrees. So we have both the angles to be equal, and their sum is also equal to 180 degrees. So now we have shown that the ABCD is a parallelogram in which all the four angles are 90 degrees. And we know that if a parallelogram has all four angles equal to 180 degrees, it is a rectangle. So since all the four angles in the parallelogram ABCD are 90 degrees, all four angles in parallelogram ABCD are equal to 90 degrees. We can say that ABCD is a rectangle, which is what we have to prove. And we know that a rectangle is a parallelogram in which all the four angles are 90 degrees. So we have shown that all the four angles of this particular parallelogram ABCD are equal to 90 degrees, and therefore that parallelogram ABCD is indeed a rectangle. So we have shown that a cyclic parallelogram is a rectangle. Okay, that brings us to the end of this chapter on circles, where we have completed all the exercise problems. We will now move on in the subsequent lecture to start with the next chapter on surface areas and volumes. Okay. And also, just a quick bit of information regarding offline classes for classes 9 and 10 CBSE Mathematics. I would like to bring to the attention of my viewers that offline tuition sessions for classes 9 and 10 for the upcoming academic year 24-25 will be commencing in April 2024, and the classes will be conducted in Chennai. Okay, so students who are from Chennai can attend the offline classes, and each batch will have a limited number of students. So those who are interested to register for the offline tuition sessions can get in touch with me via WhatsApp on this given phone number here. Online sessions can also be arranged. That depends on my availability and also on the requirements of students and how many students are willing to participate in the online session. But I will continue to add my videos on YouTube covering all the chapters of classes 9 and 10 subsequently going forward. But due to a lot of requests, I've decided to commence offline sessions in Chennai, commencing from April 2024. For those of you who are interested to join my classes offline, please do get in touch via WhatsApp on this phone number.